Hi, welcome back. In this lecture, I would like to talk about the two laws that are very important for high-performance computing. The two laws are the Moore's law and the Dennard scaling. I would like to start my lecture with a question for you. The question I have is, what do you think the Moore's law says in the original paper from the 70s? I'm sure you've heard before about the Moore's law, and the Moore's law is usually cast as the quantity x doubles every 18 or 24 months. So what is this quantity x? Is the computer performance, is the CPU clock speed, is the number of transistors per chip, or one of the both at a constant cost? And the answer is that this quantity is actually the number of transistors per chip at a constant cost. So this is from the original paper from Gordon Moore, right? It's from the 70s. You see here a figure on the right of the slide. So the Moore's law has not been true in the last decades. The improvement due to the Moore's law have been remarkable, but it's getting increasingly difficult to maintain this exponential improvement. So what are roadmaps? Well, so there are some society, particularly the semiconductor industry, that has prepared a roadmap of future trends and requirements. So there is an association called Semiconductor Industry Association that has been founded in the 77, around the first chip were made, and it provided roadmaps from early 90s. And so there is ITRS, that is International Technology Roadmap for semiconductors in place. And these are the link for the ITRS homepage and the current projection. So these slides present the projection that different studies made in a different time. So these are ITRS projection for the gate length. So this is the gate length in the transistor for 2005, 2008, 2011, and 2013 ITRS edition. So the plot is the following. So we have on the x-axis the expected manufacturing here. So now we are at 2000 around this area here. On the y-axis is the physical gate length in nanometers. So we have different colors and different lines. You see the blue lines is actually the projection made in 2005, and in green 2008, and then we have two projections 2011 and 13 that basically are overlapping, right? So we can see a few things from this graph. The first one, that the projection made in 2005 were very optimistic. So we're basically predicting that in 2021 to reach the 5 nanometer technologies, right? So you see that the projection made in 2008, so after 3 years, is actually projecting a delay of 3 years in these technologies. And then we have a delay from the blue line to the red and the black lines of 5 years, right? So today we are in this range here, so it's expecting of 10 nanometers technologies. So right now, the Intel, the last processor, they do use 10 nanometer gate length. So this last prediction are actually in line with what is predicted. So one of one of the misunderstanding about Moore's law is really about confusing the Moore's law with the performance, right? So we often hear about, the performance of the chip is doubling every 18 months as a formulation of the Moore's law, right? This is not the original Moore's law, but why people for a long time, um, why this actually was actually true for quite a long time, and why is it often confused with Moore's law with increased performance. So it's not because of the parallelism. So for most of its life, Moore's law held it on single processor performance, and Moore's law and single processor performance correlated well. So the Moore's law did mean processor performance. The main reason is that Moore's law is confused with performance is that the size and the speed are related. In particular, as the size of the gates of the transistor becomes smaller, also it becomes faster. It's faster because it's faster to switch in the transistor. So the smaller something it is, the quicker it can be changed. That is, the switch between on and off of the transistor is actually faster. And that is the reason why a smaller and smaller transistor can actually switch at a higher speed. All right, so we were going towards a smaller transistor that become even smaller, they become even faster. So this is a plot of on the x-axis we have the time from the 70s, from the first Intel processor, 2010, and the y-axis we basically have four different quantities. In green we have the number of transistor. In blue we say that is actually the clock speed, and then light blue we have the power, and then in the purple color we have the instruction level parallelism, right? That is pipelining and vectors on the processor. And you can see that the green line is so this is a logarithmic scale. That means that all this line in this scale is actually exponential. As you see, the transistor is actually increasing exponential. But the most surprising part is about these remaining lines, the blue lines, the purple lines. As you can see from basically 2005, there is a major flattening in the clock speed, and also in the power. So why is we see this flattening of the clock speed? So we saw that that clock speed. So we saw that the transistor continue to shrink, right? But why not the clock speed is increased? As I told you, if you go smaller, it's also faster to switch. So why this didn't happen, right? Well, this is due because of Dennard's law, and especially at the end of Dennard's law. So the Dennard, who is an IBM scientist in 1974, observed that the voltage and the current should be proportional to the linear dimension of a transistor. As the transistor shrank, so did necessary voltage and current. Power is proportional to the area of the transistor. So this is the Dennard scaling. Here we have the equation that is the power is equal to alpha, that is a constant, multiplied by the capacitance, multiplied by the frequency, by the voltage. So the capacitance is actually related to the size of the transistor. So as the size of the transistor shrank and the voltage was reduced, circuits could operate at higher frequency at the same power here, right? So the the C goes down because this is related to the area. So if this goes down, then the frequency goes up, right? However, the Dennard scaling ignore two important factors that become very important when go to very low size of the transistors. So the Dennard scale ignore the leakage current and the threshold voltage, which establish a baseline of power per transistor. Right? So these two phenomena are related to quantum effects. So the smaller you go, we reach the quantum scale, and there are quantum tunneling effects that lead to leakage current, right? So this can be neglected for larger size where we don't have quantum effects, but going smaller, we hit quantum effects, and the leakage current becoming an important problem. So as transistor gets smaller, power density increases because these don't scale anymore with the size, right? Because we have leakage current and threshold voltage at this very small scale of the transistor. This created a power wall that has limited practical processor frequencies to around 4 gigahertz maximum since 2006, right? So it's been roughly 15, 20 years that this is actually true, right? I just want to go back. So this C doesn't go any more down because of the size. So that's also mean that if cannot go up. So that's the end of the Dennard scaling. This is a plot representing the Dennard scaling until actually it worked, and the end of the Dennard scaling. On the x-axis, we have a time from the 80s to roughly to 2012. So each point is an Intel processor clock in megahertz, right? And these are different Intel processors. You see that from the 80s up to 2005, roughly here, the clock frequencies of the Intel processor increase linearly. Well, increase exponentially because this is a logarithmic scale. So we have an exponential increase as the transistor size goes down until a certain point that these two phenomena get important and we cannot increase anymore the clock frequency, right? So around 2004, we reach a size that where the leakage current becomes important, and we cannot increase anymore the clock frequency. So you see here basically all the processor around between 2 and 4 gigahertz. Some prediction trends from different time, different report from the ITRS. So the most important is probably the last one here, 2012, and you see that the increase of the clock is rather limited, right? So it's still around 3-4 gigahertz, right? While previous prediction they were actually looking at clock frequency around 100 gigahertz. So the question I have for you is true or false that Moore's law said the computer performance doubles every 18-24 months? Well, the answer to this is actually false. It was true before when the number of transistor per unit area at constant cost was strongly related to the performance. We saw that after 2006, there is no anymore much correlation between Moore's law and performance. This is the last question I let you to answer, just to give you some things for thoughts. If the number of transistors per unit area on the same chip size doubles every 24 months, so every 2 years, by what factor does the length of the size of transistor, assuming that is square, decrease every year? And most importantly, if we start from a length of 18.4 nanometers in 2014, what would be the projected size of transistor in 2025? And how does this compare to the ITRS value of 6.75 nanometers? So this was my last slides for this lecture. In the next lecture, we start looking at shared memory programming and shared memory programming with the OpenMP. Talk to you soon.